Hey, Denellen High School, this is Mr. Ayton back again with Electrochemistry Vodcast Part 2. This is your last Vodcast for spring break, and don't be afraid to do some extra studying on any other questions. As we come back, we'll be jumping into electrochem, and then we'll be into our review till the AP exam. So let's get to it. We're going to start off by finding out how to calculate the standard cell potential, this E with this little degree symbol. That little degree symbol means standard. At 25 degrees Celsius, it's standard conditions. Okay, and we have two metals. We have zinc and we have silver. Zinc and we have silver. This is similar to what you saw on the first vodcast, but I'm going to actually show you how I got those half reactions. Okay, and how we're going to get what we call the voltage or the standard cell potential. Okay, and in order to do this, we have to go to the standard reduction potential chart. Okay, that chart that's often on the back of your periodic table. And there's all of these half reactions, and something to keep note of, every single one of these reactions are gaining electrons. If you see, the electrons are in the reactant side, which means they're being gained, which means every single one of these reactions are reduction reactions. They're reduction half reactions. And so in this one, we're looking for zinc and we're looking for silver. You can see right in the middle of that middle of the page, you can see there's silver just jumping out at you there. Okay? And when we go in, we find our two half reactions at 25 degrees Celsius. We see we have silver plus 1 plus an electron gives you silver, and that gives you an E, or a voltage of 0.8 volts. And the other one is zinc plus 2 electrons gives you zinc solid, and that has an E of negative 0.76 volts. Now, something to keep in mind is if the overall E is positive, the reaction is spontaneous. If the overall E is negative, the reaction will need electrolysis or electricity to proceed because it is not spontaneous. It needs energy in order to proceed. So this reaction right here, this reduction reaction that we have, it is spontaneous. So we're going to have to flip one of these two reactions. Can you see which one we're going to have to flip? Of course, we're going to flip the negative because we want to make it positive. We want to overall make everything positive. And so when we flip the reaction, now keep in mind, the reactions that we don't flip are called reduction reactions because they're gaining electrons, which means the one reaction we do flip is automatically our oxidation reaction. Okay? And so when we flip it, you can see what happened. We didn't do anything to the first reaction. It stayed the same, but we flipped the second reaction, and it became positive 0.76 volts, just like in Hess's law when we flip a reaction. The only difference with Hess's law is if we multiply things by 2 or by 3 or anything, it doesn't change your voltage. And so what do we have to do? We have to get our electrons the same. Do you see the top reaction has 1 electron? The bottom reaction has 2 electrons. So what do we have to change? We got to make a 2, a 2, and a 2. We got to multiply all our coefficients by 2 in order to have the same number of electrons. But if you see, it didn't change our voltage. Our voltage is still 0.8 volts. Do not change that voltage. Okay? The voltage is independent of the coefficients. What do we do at that point? We add everything up. We add all of our reactants together, all of our products together, and all of our voltages together. And so we have zinc solid plus 2 silver plus 1s, giving you zinc plus 2 plus 2 silver solids. And you can see the zinc is going from a solid to aqueous. The silver is going from aqueous to a solid. So the silver is actually gaining in mass. The zinc is actually getting lost in mass. And it gives us a voltage, an overall voltage of what we would read on a voltmeter of 1.56 volts. And you can see there's 2 electrons that are transferred. That's as easy. It can't be any easier than that. Okay, you're going to flip one reaction, get the electrons the same, add them up, and that's it. That's all you got to do. There are some equations to take a look at electrochem in thermo and electrochem in stoich. Our electrochem in thermo equation is delta G, this is where we find out that it's spontaneous, is equal to negative N. The N is the number of electrons that we're transferring. F is a constant, it never changes, called Faraday's constant. It's 96,500 coulombs for every 1 mole. And we have our E. Our E is, of course, our standard cell potential, what we got in voltage. Okay? And so the electrochemistry with stoichiometry, we have an equation there which is current, which is in amps, that's I, is equal to Q over T. Q is coulombs, our charge in coulombs. And so let's say we know our current and we know our time. Let's just say, for instance, we produce 120 amps of current, 120 amps in, say, 60 seconds. I would have to give that to you, 60 seconds, for the reaction that we had. And so what would happen is we would multiply those together, and that would give us our charge in coulombs. Once we know our charge in coulombs, we could, of course, just do a bunch of ratios. 96,500 coulombs for every 1 mole of electrons. What did I know in this reaction, in the reaction that we just did? That we had 2 moles of electrons that were transferred for every 1 mole of zinc. For every 1 mole of zinc. Let's just say we're trying to find zinc here. And we have 63 grams for every 1 mole of zinc. It's a bunch of ratios, and we end up getting 2.35 grams of zinc. In order to produce 120 volts for 60 seconds, we need approximately 2.35 grams of zinc. And so really, guys, all this is a ratio problem from one side to the next. And so this comes with our Electrochem Part 2 questions. We're going to refer to the spontaneous electrochemical cell that I put there with aluminum and zinc. Aluminum, zinc. And you got to find out the following questions. What substance is oxidized? Which electrode is the cathode? What's the net ionic chemical reaction in the cell, which means what is the final reaction in the cell? Which metal gains mass during the reaction? What's the standard cell potential in volts? How many electrons are transferred? What's the delta G? What's the Gibbs free energy at standard conditions? If the reaction produces 240 amps for 120 seconds, how many grams of aluminum would be used? Guys, make sure you go to your standard cell potential chart in order to figure out that the 2 half reactions you have to start at. And again, if you want some extra credit, you can email me your answers. Just go to MrAyton.com and go to the contact up in the upper right hand corner. You can email me your answers over spring break if you want some extra credit, or if you want to turn it in the first day you come back from spring break, that's fine. Again, guys, make sure you do some extra problems over spring break. Don't just do some electrochem, and start your review now so that come May, we rock this test. Have a great spring break, guys. I'll see you when we come back. Thanks. Bye.